Got it. All right. Now it is my pleasure to introduce Carly Howett. She did her PhD in Oxford, stayed there a while for a postdoc, and then went all the way to the other side of the ocean in Boulder, Colorado, where she also did a postdoc, but then climbed the ranks, senior scientist, and became an associate professor there. Clearly, she missed the beautiful British weather, so she came back a couple of years ago to Oxford, where she's an associate professor now, and she presumably has the most fun job in the entire world because she gets to play with space robots. She's involved in lots and lots of space missions that are studying our own solar system, more specifically the icy worlds in our solar system. So today she's going to talk about her games with the space robots. Carly, all yours.
Thank you. Thanks for that introduction. And I owe everyone there an apology. I was supposed to give this talk in January, and it was the same week that my daughter brought home COVID along with all the other children in her classroom. I think it was I think there were 64 children in a year group and only 2 kids were at school that week. So it was a lot like everyone that's been through it. It wasn't terribly pleasant. So thank you for rescheduling. I think it's much nicer for everyone that I'm giving it now and not then. And thank you for giving me the excuse so I can legitimately go and have a glass of wine after this, because, you know, everyone else is, right? All the cool kids are. So thanks for that too. So I kind of wanted to give a little bit of an overview of sort of the work that I've been doing without getting into too much detail. But I thought one of the things that's kind of fun I've been thinking about recently is sort of all the stuff that's gone wrong, right? I feel like it's a bit like Facebook profiles, right? Everyone always posts these wonderful photos of them with their gorgeous children and their happy lives, but no one posts all the, you know, the photos that went wrong in the meantime. And I've been sort of trying to think back about the things that have gone wrong in my work on different space robots to try and encourage others, especially some of the students and postdocs. You know, what only gets written up is all the stuff that works, but there's a lot of things that go wrong in the meantime. And I thought it'd just be kind of fun to talk with that, a little bit that sort of spin to it. So I thought I'd start by showing you a picture of what Beagle 2 was supposed to look like. Now, for those that don't know, Beagle 2 was a UK-led mission that was to Mars. And it launched back in, I think, 2003 upon Mars Express. It was supposed to land on Christmas Day that year, and it never called home. It must have been 2001, and it never called home. For the longest time, we didn't really know what had happened to Beagle 2. So I was a student at the time, and I was given the opportunity to work on the stereo imaging cameras when I was doing my master's at University College London. And these cameras needed a wiper to move the Martian dust off of their lens. So I got to develop a windscreen wiper for Mars, which was a pretty fun master's project. But alas, we never found out whether it worked. And for the longest time, there was an idea that the airbags probably didn't work on Beagle 2. It was sort of done on the cheaper side. They weren't really able to test the airbags very well. But actually, the US led high-rise camera took this image, which actually showed Beagle 2 landed successfully. It wasn't the airbags at all. But what actually happened was that the sun, you could see those solar panels, they were supposed to unfurl, and the final solar panel didn't unfurl. We don't know why, but that solar panel was hiding the high gain antenna. And so without its high gain antenna, even with power, it was never going to be able to communicate with the Earth. And one of the sort of funny coincidental things was this image was taken in 2015, which was way after I'd finished my PhD, and I'd moved to the States, as was said, and I was starting to work on a mission called New Horizons. And in 2015, was the flyby of New Horizons past Pluto. And so it'd taken 9 years between launch and New Horizons getting to Pluto. Pluto's a long way from the Earth, as we all know. To give you some orientation, it's embedded in the Kuiper belt, so a bunch of small objects on the distant side of our solar system. And at the time, Pluto's got this highly eccentric orbit. So at the time, it was kind of nearly in the elliptic plane, and New Horizons was due to fly by it. But 10 days before the encounter, so the encounter was scheduled for July 14th in 2015. So on the 4th of July, when you're in the States, most people know that's an American holiday, it's Independence Day. We got a safe mode. So we basically got this sort of blue screen of death back from the spacecraft. And what had happened was we, as a team, had asked too much of the spacecraft. We asked its software to sort of the equivalent of save and copy at the same time, and it didn't like it. Thankfully, this time though, the spacecraft called home, and a safe mode on most spacecraft means it stops doing any activity, and the only thing it focuses on is calling home and saying, ha, things aren't okay, can you please help me? And we were given enough information. We knew what the timestamp of the safe mode was. We knew what it was doing at the time, and so we were able to reboot the spacecraft in time for the encounter sequence to start. So we did lose some data. We lost about 3 days worth of data because the light time to get to the information to get to the Earth and then communicate with the spacecraft was about 9 hours, I think, at the time. So it makes talking to the spacecraft a very long-winded process. You know, you send a command and then you go and get a few hours sleep and you wait to see what it says back. We had some engineering models on the ground that we're able to test with, but it was fundamentally quite a worrying period. But all was well, and this is a movie I just really like showing. I hope it works. So this original image was the best map that we had of Pluto. So it was constructed by various HST images taken by Mark Bowie. And you can see that it's kind of blobby, right? There's some dark bits, there's some light bits, but it's a bit hard to get excited about such a blobby image. And after we'd flown by it, this was the level of detail that New Horizons sent back. So this is a true color image. If you were sitting on New Horizons, we think this is what your eyes would perceive Pluto to look like. So quite brown, quite gray, and quite beige. Lots of sort of hydrocarbons. If you stretch this image, so this is an enhanced color image now into the into the IR, and slightly sort of not quite UV wavelengths, but more blue than your eye can see, you get this enhanced color image. And this is a really beautiful image because it shows you just how complex Pluto is. But each one of these colors is a different composition. Without doing any other analysis, you can see what a crazy place it is. But we have some. And the other thing that jumps out of you is this heart-shaped region, which is sort of just off of the equator of Pluto, and especially on this sort of left ventricle of the heart. I hope you can see my cursor. You can see it's really crater-free, and that was a huge, huge, huge discovery that was made by New Horizons, because it meant that at 40 AU, you know, a long way from the sun, we're seeing active geology at this moment in time, or I guess in 2015 technically, but you know, there's this region is made from nitrogen ice at Pluto's temperatures at about 70 Kelvin. Nitrogen ice is very soft. So you could think of it as sort of a Mr. Whippy ice cream, right? Like if you poke your finger into a 99 flake and pull it out again, that sort of all the ice cream is so soft, it's just going to kind of collapse in and cover that hole, that crater. And the same thing pretty much is happening on Pluto. This ice is so soft, anytime anything hits it, it doesn't make a crater, it just sort of slops back. And we actually know there's overturning there. There's the ice is so close to its triple point that it's able to overturn, and you kind of get a lava lamp effect. So just zooming in on some of the cool stuff that we found. So looking at this yellow box, which is at the top of that heart-shaped region, this is really where that nitrogen ice, that soft ice, hits water ice, and the water ice there is so cold that it's like rock. You can build mountains out of ice, water ice on Pluto. And so you can see that the ice itself is sort of flowing like a liquid. You can see the sort of eddies as it goes by this sort of sticky out bit of the water ice mountains, and as it moves towards this shoreline. This is a zoom in on the polygonal cells, so these overturning cells, and you can see that this gunk is getting caught in the edges of this of the cells. It's basically kind of gets pulled there as the ice then gets pulled down, and this sort of sits on top, it floats on top. We don't know what it's made from, but it very clearly details the edge of these cells. We had an infrared camera on board, an infrared spectrometer called LISA, and from that we were able to derive the the composition of Pluto. And so you can see there's a strong difference in distribution for, like, if you compare nitrogen ice and water ice. The water ice is mainly around this dark region, which is informally called Cthulhu. And then the nitrogen ice is a lot more in that sort of heart-shaped region. The methane is a lot more ubiquitous, except for, again, that dark Cthulhu region. And really, we only see carbon monoxide in the overturning region. This just highlights the same thing, but in a little bit more detail, just showing you where the water ice is observed. And this was really important because, as I was talking to some of the students earlier, you know, observing water ice on other planets through the Earth's atmosphere is a really hard thing to do. And we've never actually been able to resolve water ice signatures on Pluto, even though it's postulated that they must be there. And so to discover them, certainly in the concentrations we saw, was pretty exciting. So looking at the mountains a little bit more, these are the Algesi Montes, which is on the edge, on sort of now on the southern edge. We looked at this northern region here, and it's just a really interesting kind of chaotic region. If you've ever looked at Europa, it looks a bit like chaos terrain, like broken up blocks of sort of icebergs, really. And you can see, if we zoom even more, you can see color varying across blocks, and almost mass waste, like the stuff is some sort of slop, the steeps and collect at the bottom of the mountains. We're still not really sure that is, but really some form of hydrocarbon. And finally, an Ixing mountain. This is Rights, and it's a mountain with a hole, which to mean goes with Pluto. So it's probably a cryovolcano. And there's a new paper out by Kelsey Singer in Nature Communications this week, detailing, giving more evidence for Wright Mons being a cryovolcano. But we think that at some point in Pluto's recent geological history, this was active from the deposits that we see on the surface. It wasn't active when New Horizons flew by. We saw no evidence of current activity, which was a bit of a shame because that'd be super cool. And then finally, after we had a closest encounter, we looked back at the target, we looked back at Pluto, and just got these absolutely stunning images where the atmosphere of Pluto looks so well defined. I mean, if we zoom in a little bit more, you can see the haze layers. Each one of these layers we think is real, and it's just a slightly different composition. And you can see just how complex it is. And this is one of my favorite images of Pluto. This is us looking back in, again, true color now. And so it's backlit by the sun. The sun is directly behind Pluto. We're kind of in eclipse. And you can see that Pluto's sunrises and sunsets would be blue. So if you were on Pluto, it wouldn't be red sky at night, Shepherd's Delight. It must be blue sky at night, Shepherd's Delight, whatever that would mean on Pluto. But just a really cool result. And of course, I'm a moons person, so I couldn't talk about the Pluto system without talking about moons. And this is one of my favorites, Charon. So it's about the same size, almost about the same size as Pluto, slightly smaller, with this huge crack across the surface. And this, of course, couldn't be resolved from the Earth at all. So what has probably happened is Charon froze from the outside in. It's mainly water ice. So as the core froze, it wanted to expand. And eventually, to do that, it caused so much pressure on the outer shell that the outer shell cracked and caused this big chasm, which then, of course, flash froze immediately. This red splotch on the top of Charon is real. And it's really interesting. So this is the best view we had of Charon. We didn't get to see the southern hemisphere. And so there was different ideas about what could be caused in this red splash. You know, it sort of looks like it's co-located with a crater. So maybe whatever hit it might have been red. Or perhaps for some reason, you know, there's another mechanism whereby Charon's north pole is red. And we think it's the latter. So this is just the same image now reprojected from a polar perspective. And we think that actually we're seeing the same sort of darkening on the southern hemisphere. So it's a bit hard to see. Like I said, it wasn't in daylight. It was very hard to see the South Pole, but we co-added a lot of images. I think it's 99 images are co-added. And then we compared what we observed to a photometric model. And that's what you're seeing here. So this is the black and white image that's kind of co-added. This is what we would expect if it did have any reddening. And what you actually see is when you take the difference, you can see darkening towards the southern hemisphere. So of course, this is black and white. It's hard to say it's really red, but we do see when you look at reflectance geo with the left, which is bottom right-hand plot here, you can see that the the model, which is the dashed line, sort of follows a very similar trend to the observations, which is shown by the crosshairs. So we think what is happening is Charon North and South Pole have hydrocarbons that have been snatched from Pluto. Pluto's atmosphere, of course, is escaping. Charon's very close to it. What's happening is some of the hydrocarbons happenstance to make it to Charon. Charon's very, very cold at its poles. And so basically the hydrocarbons there are then trapped, and they're altered by sunlight to make them longer chain, which means they can never ever escape, and they also get darker. And so we think that Charon has dark poles because it's basically nabbing some of Pluto's atmosphere and photos, and it's being changed by sunlight. The last target that we looked at is Arakoth, and this was, I was actually talking to some of the students about this target as well earlier. So Arakoth is a cold classical Kuiper belt object. It's about 32 kilometers across, and you can see that it's bilobed. So it has two lobes sort of attached by what we're referring to as a neck-shaped region for somewhat obvious reasons. A lot of work has been done on this subsequently, and I'm not going to get into most of that. But one of the things that sounds boring, but is actually really cool, was that Arakoth is a really standard cold classical Kuiper belt object. Now, you always think it's good to go and visit special things, right? But if you look at if you're looking at one type of a body that's, you kind of want it to be similar to all the other bodies, because then you can infer things about it. If you look at an end member of that type, it's very difficult then to infer anything about the other members in there. So it's about the same size, it's about the same color. So the cold classical colors are very red, and Arakoth was too. And so you can see the cold classical Kuiper belt objects are shown in red here. Arakoth sits in the middle, and the full Kuiper belt objects have a spread. So cold classicals just mean that they don't have a steeply inclined orbit. They have a low orbital tilt, and so it's not cold in the sense of temperature. It's cold in the sense that it's not inclined. So talking of small objects, that brings us nicely to the next mission, which is Lucy. And Lucy is stepping inside the solar system now. And what it's primarily interested in is the Trojan asteroid. So these are shown here in purple. There's two swarms, the L4, which is shown at the bottom, and the L5 swarm, which is shown at the top. And one of the reasons to go was that we've never seen these type of asteroids ever. Right, so all of the other small bodies in our solar system have been investigated by spacecraft at some point or the other, but the Trojan asteroids haven't. They're dark, and at Jupiter, it makes them hard to look at from ground-based observations. So yeah, they're split into two types. We're not really sure how many they are, and one of the things that they're really interesting is that there may be remnants of solar system formation. And this is an example of the NEAS model. I'm sure many of you are already familiar with this, but this is one idea of how the solar system formed. And so the sun's in the middle, Jupiter, Saturn, Neptune, and then Uranus. And for those keen-eyed amongst you, you'll realize that in this model, Neptune and Uranus has switched from what they are now. And so the main objects are all the little things that happen, the leftovers of solar system formation. But there's this huge cataclysmic event that happens. Neptune and Uranus swap places, and it caused all of these small objects to fly across the solar system. And I can show that again because I was sort of talking through it. So, and we think that the Jupiter Trojan asteroids sort of formed as part of the outer green belt, but then got trapped by Jupiter as everything threw across the solar system. And so other than this sort of move around the solar system at that time, they've been relatively unchanged. The L4 and L5 swarms are very stable. They were able to stay there for a long period of time. So they formed probably out at like 30 to 40 AU, but that have then been trapped at 5 AU near Jupiter subsequently. So what do we know about them? Well, the answer is not a lot, and the next few slides are going to highlight that. So we know that they can be split into three spectral types: a C-type, P-type, and D-types. The D-type asteroids are reddish and thought to be more primitive, and the C-types are gray and maybe formed closer to the sun. And the P-types are kind of somewhere between those D and C types. We can also split them out by sizes. And you'll see that the size distribution is quite different between the different the different sizes. So between the big ones, 100 kilometers and bigger, it's mainly the DMP with very few C types. And then as you get smaller, you start seeing the C types emerge. We don't really know what that means. It could be that C's are fractions or sort of remnants of the DMP types, but we don't really know that. And then finally, we can think about where they're located. So now you're looking at the mass of these types. So if you added all of the C-type asteroids together at a given location, what would its total mass be? And so you get 3 plots, and you can see the C-types, which are the solid blue lines. I've lost my cursor. The solid blue lines here are outwards of Jupiter. Jupiter's at 5.2 AU. The D types are spread quite evenly around Jupiter, so that's the thin blue line that's towards the top. And then the P types are the dotted black line, which peaks downwards of Jupiter. Again, we don't really know why. We just know that they can be categorized in this way. And then finally, we can think about them in terms of their brightness. So you're looking at visible albedo versus IR albedo, and here it's the 3.1 to 3.8 brightness. But plotting the X equals Y line is shown in dotted lines. So you can see that they're kind of brighter in the IR compared to the visible. And you can, one of the nice things about Lucy's targets, which is shown by the big orange dots compared to the others, are that they really do cover the range of albedo spread that you see in the Jupiter's Trojan asteroids. We're going to talk a little bit about the targets in a minute. All right, so this is Jupiter, this is Lucy. And just in case you were in any way you weren't sure where Lucy was made, they've handily put a big American flag in the background, as is the American way. It's about the size of a minibus, and it was funded through NASA on their discovery budget. There's 6 targets, one of which is a binary, and then we have a bonus target, which is Donald Johanson, which is a main belt asteroid. So we're going to fly through the main belt, which is the sort of asteroid belt between Mars and Jupiter, en route to the Trojan asteroids. So we're going to use this as sort of a warm-up act for our spacecraft, like how do we observe asteroids? How do we use Lucy to observe asteroids? But we'll get some good science as we go by. One of the things I didn't touch on actually was how Lucy got its name. So Lucy is the hominoid that's one of the oldest human, I think it's the oldest human fossil that has been found to date. And it really helped anthropologists connect this sort of the human evolution. And so Lucy is named after that fossil, and because we hope it's going to enable us to sort of trace our own fossils history, our own evolution of our own solar system evolution rather. But the founder, the person who led the team that found Lucy, was called Donald Johanson. And so the main belt asteroid that we're going to fly by was named after him, which is kind of a nice nod back to its namesake. And then we've got our targets, our L4 and L5 targets. So I'm going to talk a little bit about the details of each of these, but you can see just from this table, we've got different types. We're hitting the C, P, and D type asteroids. They're very different sizes, anything from handfuls of kilometers to hundreds of kilometers wide. And we've already talked a little bit about the albedo. So let's look at these targets all at once. No, I don't want a big flash player. Okay, sorry. All right, so this is our trajectory. It's the frame rotates with Jupiter. So you could think of sort of everything being static with respect to Jupiter. So of course we launched from the Earth. That was in October last year. And I've got some photos of that in here, I think, to show you. And then we'll fly by Donald Johanson in 2025. So we're kind of going to do a couple. We swing around the Earth a couple of times. We've got some Earth gravity assists. Then we fly by Donald Johanson, and then we go into the the L4 Trojans, where we have the Eurybates, Polymele, Lucas, and Orus encounters. And then we come out of the L4 Trojans and we swing back around the Earth, sort of this figure of 8 almost sort of trajectory. And then that pushes us into the L5 swarm. And that's when we have our last encounters, which are with Patroclus and Menenius, which are a binary system, and they're both very big in 2033. So this is obviously an artist's impression of what we think they might look like. So let's start with Eurybates. So Eurybates is really interesting, especially for a lot of British scientists, because there's a lot of meteorite work that's done here, and we think Eurybates is the largest member of a major disruptive collisional family. So we've never looked at the sort of the parent body for such a family before, and so it's going to give us an idea of what the big remnants of a collision might look like, and a better understanding of those collisional processes. It's also a C-type, and we already talked a bit about how that's rare. We don't really know what a C-type is. We already sort of mentioned perhaps the D-types disintegrate and form C-types eventually when they're hit. But Lucy's going to help us understand a lot more about C-type asteroids through Eurybates. Polymele is the next one. So Polymele is much smaller, and we think it's actually a fragment. Oops, I've done these in a weird order, so I'm sorry. Oh, no, okay. So Polymele is a fragment, we think. So whilst Eurybates is kind of the big end member of a collision, Polymele is sort of a small one that came off of it. And the difference between Patroclus and Menonetius, which are much bigger, and Polymele is about 160 times different. So we're looking at very different targets. Patroclus and Menonetius are really interesting. I already said they're near equal mass binaries. These are the best observations we have of those right now. On the bottom, sort of obviously not the top, that's just a model. And that was taken using Keck AO back in 2006. And the binary systems are really interesting because in order for them to remain binaries, they must be undisturbed. Right? They probably form that way, and it wouldn't take much to disrupt them. So we think that this gives us a strong indicator that they're primordial objects, but we don't really know how they're formed, and so we're going to finally get an insight into that by flying by them. Moving on, Lucas. So Lucas is a D-type asteroid, which means it's slightly redder. And Lucas is just really strange. So this is a light curve that we've seen from the Earth. So lots of observations were made of Lucas, and you can see all the different colors of the different observations. When you try and make sense of how Lucas could produce those light curves at the different timestamps, a period like this makes the most sense. But it's strange, right? So to explain what this is just the amount of reflected light that the amount of sunlight Lucas is reflecting. And so if it was a complete sphere, it would reflect the same amount of light the whole time. The only thing you would see less of is your perspective with Lucas, right? But what's happening is you see this really large dip here. And so what does that mean? Well, it probably means that it's very asymmetric. So you could imagine that if you have a very large face that's facing you, that's going to be able to reflect a lot of sunlight. But if you have a very narrow face that's facing you, it's going to reflect a lot less. And so what you're seeing here is a strong indicator that that Lucas has got very different size faces as it rotates. It's also got a very long period. So 53 hours is kind of pretty strange. So maybe there's a satellite involved, and that might explain some of these weird periodicities. Sorry, the period is 500 hours long, but there's the potential of a satellite in here with a shorter period. And it wouldn't be surprising. We've seen Eurybates having a satellite. So maybe satellites are actually more common in the Trojan asteroids than we originally thought. But once we get there, we'll know for sure. Orus is basically, we don't really know that much about Orus at all. I think this is a movie. Let's see. So this is an occultation observation. So what you're going to see is not Orus itself, but rather Orus blinking this this star out. And I'll show you again because it's not very obvious. So this is the star to look at right in the middle of the field of view, and you can see it blink out. It's very hard to observe these. Occultations give us one of our best ways of doing it, and from this occultation, we could confirm that the diameter is about 55 kilometers wide. Oops, sorry. So we don't really know much about it. So this is kind of our summary of the targets that we're going to see. All right, so we launched. That was good. It launched from Cape Canaveral, the Kennedy Space Center, in October last year. obligatory selfie in front of the spacecraft, because if you go there, you kind of have to do that, and obligatory launch videos, because everyone likes seeing a launch video. If it starts, there we go. I thought about putting up the one that I took, but really this doesn't involve me going, it's working a lot. Right. So one of the things I'm happy to report that didn't go wrong in this talk was Lucy's launch. The fiery bit stayed at the bottom, the pointy bit stayed up high, and we launched right at the beginning of the launch window, which was so great for so many reasons. It was great on a scientific level because it meant we had the most optimal of trajectories. We actually didn't have to do any trajectory correction maneuvers because the launch was so good. It was also really good because the launch time was at 5:30 in the morning. We'd gone out to Florida, and so it's like catching a 5:30 flight, right? Like if you work it all back, okay, so we're gonna have to clear security at 3, and then that means you've got to leave your house at 2, which means you've got to be up at 1. We had 2 young children, and I'm not sure how many 5 or 1:30 a.m. starts they could have managed, but we got to all see it, which was pretty fantastic. If you've never seen a light launch, never get the opportunity to do so, do jump at it. Oops. So on to problems. We haven't encountered any problems in the last few slides, so it must be time to talk about it again. And the problem with Lucy is its solar panels. So Lucy is solar powered. It's the first time these are the biggest solar panels that have ever been flown into the outer solar system. Flying something to Jupiter on solar panels is relatively rare. Certainly is only possible because of new technology. These are big. They're 7.3 kilometers, and I like this image because it sort of gives you the scale of what they are. And you can also see a little bit of how they unfurl. I think, is this a video too? Yes, it is. So this is a ground test that's obviously been sped up, and there's support above it because obviously we're doing the test in gravity and Lucy wouldn't have to do that. But the important thing to note is this lanyard, this metal lanyard. Sorry, I'm looking at the screen because that's where it's on both. Anyway, so this metal lanyard that pulls the spacecraft around, sorry, sort of unfurls the solar panels. And what we think happened after Lucy launched was that this lanyard fell off the spool. So you can imagine it's a bit like a fishing reel, right? Like you're reeling this lanyard in, and it fell off the spool. And when you do that, the torque that you require, the force that you need to apply to that spool to keep that lanyard moving in, gets higher and higher and higher, and eventually it hit a limit and stopped. So this solar panel didn't latch, basically. So there's some good news stories here, right? The spacecraft is healthy. The solar panel is open enough to power the spacecraft. One completely latched, the other one is mostly open. So we consider that power positive. But the bad news is we're starting to understand much better what the effect of this floppy solar panel is. So the solar panels weren't designed to incur the sort of torques that you put on a spacecraft when you fire main engines, with it being unlatched. So we've done a lot of engineering analysis. We know that all of the 10 gores, the gores are sort of a single pane of these solar panels, are producing power, so they're not stuck, but we think they're just sort of not quite unfurled. So it's not that 2 are stuck together and we're going to damage something by sort of pulling it apart. It's just that lanyard wasn't able to open them all. Now we do have a redundant motor. And we weren't using our single motor on like full whack. So if we say that the motor goes from sort of a pulling power of between 1 and 5, we were using it on a 3, but we also have an additional motor. So, we could use one motor on a level 5, we could use both motors on level 5. We've got a lot of wiggle room there, and a lot of work is being done to try and figure out what the right thing to do is. And actually NASA made the decision just last week that we're going to try it. We're just going to try applying a little bit more torque and seeing if we can latch the solar panels. And so that's actually happening on Monday. So hopefully there'll be good news coming out We're going to do it in 2 parts. So the first time we're just going to apply a little bit more torque and seeing if it moves the amount that we think it's going to. And if that goes to plan, then we'll apply even more and try and get it to latch. If in some of the engineering tests, what's actually happened was we had some breakage in the motor itself, but it's one of those things like if the motor breaks once it's latched, we don't care because we're never going to use the motor again, right? So it sort of might be worth risking breaking the motor just to try and get it to latch, and that's some wiggle room that we need to go into. All right, so I'm cognizant of the fact that I've probably got about 5 minutes left. I was debating whether to talk about Europa Clipper, but I think I'm going to mention a few fun things. So I'm also on Europa Clipper. I'm a co-I of the thermal instrument. And for those people that don't know, Europa Clipper is a NASA mission that's a strategic class mission, which is what we used to call a flagship mission. So it's big, is the takeaway. And it's going to Jupiter's moon, Europa. And I'll talk about why Europa is interesting in a minute. This last year, NASA announced that it wasn't going to launch on an SLS, which, for those people that don't know, SLS is NASA's own new heavy lift vehicle. It's never been launched. So, you know, in the scheme of not wanting things to go wrong, I was kind of glad that we weren't going to be the guinea pigs for that, but instead we're going to launch on a SpaceX Falcon Heavy, and that's going to be in October 2024. The bottom left-hand plot just shows you some of the instrumentation. This thing is big. You know, it has two cameras. It has the thermal instrument. It has a radar and a UV instrument. It has magnetometers. You know, this is a beast. We're going to be flying. We've got an Earth gravity assist and a Mars gravity assist, and then an Earth gravity assist, and then we're out to Jupiter, arriving there in 2030. So Europa is a really interesting place. We think that it could well have all of the ingredients for life. We know that it has a liquid water ocean. We learned that from Galileo. In actual fact, it has much more than all of Earth's oceans underneath its icy crust. We think that it has the essential elements for life. We've seen salts on the surface. One of the ideas is that, you know, it could have all of the things that we need for life to exist. It has chemical energy. We know that there's tidal heating from below. And so maybe just like the video that's been shown, you know, black smokers could exist under the ice shell. So these are regions of these. This is a video from deep inside Earth's ocean. The light that you're seeing is because they took lights with them. It's not sunlight. And this is a region that conceptually should just be void of life, right? It's very deep under the ocean. You know, how can life possibly exist? But there's these hydrothermal vents that provide the chemical energy and the heat for life to exist. And as you can see, it's sort of somewhat teeming with life. And there is an idea that same sort of things could be going on Europa. And then stability. We think Europa was formed a long time ago, and it's had time for life to evolve. And so it's been simmering away, if you like, for 4 billion years. So the Europa mission is to explore Europa to investigate its habitability. We're not going to land on the surface. This will all be done remotely. But we're going to be looking at the ocean and its ice shell. And then we're going to be using data to infer its composition, its geology, and also do some reconnaissance. And reconnaissance is we've been talking about going back and landing something on Europa for a very long time. But you want to know with a system that might be hosting might be hosting life, that you're not going to do any damage. And so making sure that we understand what the surface is really like, but also whether it's safe for life, potential life there for us to go and investigate is good too. One of the things I'm not going to talk about too much is that we think Europa might have plumes. They've been seen somewhat sporadically. They're still slightly debated. But again, plume reconnaissance would be really useful because by flying through the plumes, you get to sample what's probably subsurface ocean material without having to drill into the subsurface. So you kind of get to sample this ocean material without potentially doing any damage to any ecosystems that are existing. The payload is built and it's now being integrated. So some of my personal favorites, I'm on the eThemis system, which is being built at Arizona State University. And that's the flight instrument on the right and the filter assembly shown. And then I am still connected with the South Research Institute. That's where I was before, where they're building the ultraviolet spectrometer with the PI's Kurt Rutherford there. And so we have images of that being pulled together too. So it's starting to get real. But there's still a long way to go. This is the nightmare schedule, which actually doesn't look too bad. This line isn't quite right. It's now, of course, we're now within sort of May 2022. So we're getting to the end of the timelines. But the point is, there's still a lot to do, and there's a lot of things that could possibly go wrong. But fingers crossed not. So to conclude, space is hard. Things don't always work out the way you want them to. New Horizons done amazing science, and we've just learned that it's been funded to do, it's got an extended mission. It's going to be doing a lot more helio science, a lot more astrophysics, but also some planetary science too. We hope that we're going to be able to observe Neptune and Uranus, for example, from that target. So look out for those images as they come down if that's of interest to you. Lucy successfully launched. It's en route to the Trojan asteroids, albeit with a slightly floppy solar panel at the moment. And Europa Clipper is nearing launch, so fingers crossed for smooth sailing for that. So thank you to everyone. Again, I apologize that I wasn't able to give this talk in January, but in a way it kind of worked out because a lot more has happened, especially with Lucy in the meantime. So it's a better update because of it. Thank you.